Hello and welcome to this lesson on soil compaction, specification, and control. The video covers the shown four learning objectives. So we'll learn about how to specify the soil compaction requirements, the compaction characteristics for different soil types, the calculation process for compaction application quantity and rate, and finally how to measure and control soil compaction on site. Let's have a quick recap of some soil properties. We covered in an earlier lesson the three different soil states: banked, loose, and compacted. In all these states, the soil has the same weight and volume for the soil solids and water, but the air volume swells in the loose state or shrinks in the compacted state. Here are four of the many weight volume parameters that we can use to describe a soil type. For the compaction behavior, we discuss a lot the dry unit weight or density and water content. Compaction is the process of shrinking the air voids within the soil to increase its density by applying a mechanical power in different forms. We need to make a distinction here between compaction and consolidation. Consolidation refers to the process of water removal from the soil, which can be very problematic in cohesive soils that can cause differential settlements under a structural foundation. The soil is compacted to increase its strength, reduce its future volume variations, and decrease its permeability. Soil strength and volume variation are very critical aspects for design geotechnical structures like foundations and retaining walls. Soil permeability is critical in designing and building earthen dams. Soil density has been used to measure, specify, and control the compaction levels. The specifications of the soil compaction are based on the compaction curve that's unique for every soil type. The compaction curve shows the relation between the compaction level and its main controlling factor, the soil moisture content. And this relation follows a downward concave shape where the soil density increases with the moisture content until an optimal point and then drops down. This means that too much moisture and too little moisture do not result in the best soil compaction. The maximum compaction can be achieved at a specific moisture content that can be identified in the lab, but is it realistic and feasible for the contractor to maintain this moisture content in every part of the compacted soil fill? Precise control of the compaction quality is not possible on site. This is why specifications typically give an acceptable range of water content that is around the optimal moisture content with plus or minus 2%. Also, the specifications acknowledge that the compaction performance of the lab test cannot be achieved on site. So contractors are required to achieve a compacted dry density that satisfies a threshold a little under the lab maximum dry density. This creates a sweet spot of compliance for the contractor to provide an acceptable compacted soil. Let's now see how these compaction curves for different soil types are developed using the Proctor tests. Proctor test is the most common standard soil compaction in identifying the optimal moisture content and corresponding dry density. There are two versions of the test: the standard Proctor test and the modified Proctor test. Both tests are standardized by the American Association of State Highway and Transportation Officials, AASHTO. The standard and modified Proctor tests share the same procedure, but with variations to the sample preparation and applied compaction energy. For the standard Proctor test, the soil is placed in a cylindrical steel mold in 3 equal layers, where each layer is compacted using a standard hammer weight that's dropped from the same distance. After all soil layers are placed and compacted, the dry density is measured. This process is repeated for different moisture content to obtain the compaction curve and identify optimal moisture content. The modified Proctor test has a similar procedure, but the soil is placed in 5 layers, and each layer is subjected to more compaction energy by increasing the hammer weight to 10 pounds and the fall distance from 12-inch to 18-inch. This means that the compaction energy in the modified tests is almost 5 times greater than the standard test. This graph shows the difference between the compaction curves of the standard and modified Proctor tests due to their compaction energy difference. The modified test results in a compaction curve that is higher in the graph, with more dry density that is achieved by less optimal water content. This has great implications on the construction methods and compaction equipment that the contractor needs to select. Standard Proctor test is generally used for fills requiring the minimal subgrade compaction, such as small parking lots and building structures, while the modified Proctor test is generally used for fills that will support large loads, such as roadways and airport runways. We should also understand the impact of the adapted Proctor test on the equipment and resource needs on the site. Modified Proctor tests sets higher standard for compaction quality by increasing the possible maximum dry density, but that will require heavy, strong compaction equipment to deliver the required power. On the other hand, the standard Proctor test will allow using a smaller compaction equipment, but will probably result in the need to apply more water to the soil to reach the larger optimal moisture content. Soil types exhibit different compaction behavior, as we can see in this graph. Coarse granule soils like sand and gravel have sharp, steep compaction curves, while cohesive soils show more a flat compaction curve. This means that the compaction quality of granule soil is very sensitive to the moisture content. Also, granule soils provide higher maximum density, and this makes them great material for the subbases and bases under structural elements like foundation and roadway pavements. The big question here: how can we control and measure the quality of the soil compaction on site? We have here some of the traditional field tests of soil compaction, but will not cover these tests in details as they are typically covered in the soil mechanics courses. The sand cone and balloon tests utilize basically the same fundamental concept of measuring the weight and volume of a surface sample of the compacted soil. In both of these tests, the soil sample is taken to the lab to weigh and measure its water content. To calculate the volume of the sample, one test uses sand while the other uses liquid to fill the void left behind the taken sample and measure its volume. The nuclear gauge test utilizes basic principles of nuclear physics to measure the soil density and moisture in an efficient and non-destructive approach. The device depends on inserting a gamma photon source in the soil and sensing these photons using detectors on the surface of the soil. The device uses the Compton effect of gamma ray scattering from the soil density measurement and the hydrogenous thermalization for determining the moisture content. The nuclear gauge is a very efficient test, but it comes with its own compliance burden due to dependence on handling and using nuclear material. We have seen that the soil moisture content is very critical in having a quality compaction. We will cover now how the soil water content is managed and in typical fill and compaction operations that don't enjoy the controlled lab environment. We will cover some critical factors for contractors to consider when trying to match the site soil water content with the lab optimal moisture content. Typically, the soil used as the fill material doesn't come with the desired moisture content from the borrow or cut site. It can come with higher or lower moisture content. If the fill soil comes with lower moisture content, then the contractor needs to apply water to the soil to increase its moisture content. This can be done by truck-mounted or towed water distributors, which is the typical method used on earthwork projects. Another way to apply water to the soil is through ponding, which is not that common and it's hard to control. On the other hand, if the borrow soil has more water content than needed, some work needs to be done to remove that excess moisture from the soil. This is done by simply leaving the soil to air and let the moisture escape over time. A more aggressive approach is very wet and plastic soil types is to use lime or fly ash to stabilize the soil before compaction. In deep foundation, dedicated dewatering pumping systems will be needed, especially if the foundation level is close or below the groundwater table. Typically in earthwork projects, rippers or graders or towed disc harrows are helpful to mechanically loosen the soil and increase the aeration process to reduce the soil moisture. These same equipment are also used in agriculture to prepare the soil for seeding after long and wet winter seasons. In the case of water application, it's very critical to know how much water to apply for the volume of the soil to be compacted. This water application volume is calculated by multiplying the weight of the compacted soil and the water content change. The compacted soil weight is calculated by multiplying the desired dry density in pound per cubic foot and the compacted volume of the soil fill in compacted cubic foot. This is in pound per cubic foot, gamma df. While the delta water content is calculated as the difference between the desired water content of the fill and the pre-existing water content of the borrow soil, the 8.33 constant is the weight of 1 gallon of water in pound. After calculating the total volume of the water application, we need to calculate its application rate to communicate to the water distributor driver how many gallons to spray in every square yard. The formula for the water application rate looks similar to the one we had for the volume calculation, but we use the thickness of the fill instead of the volume as we adjust the units from square foot to square yard. The fourth factor to consider is the weather, to account for climate conditions that may require adjusting the water application. cold, rainy, and cloudy weather requires thorough soil mixing and stabilization of the soil. On the other hand, hot, dry, sunny, and windy weather may require additional water application to account for extra evaporation or aeration. In desert climate, it's suggested to increase the specification's recommended water content by around 6%. Finally, the soil needs continuous mixing and blending to make sure the moisture content is achieved uniformly over the fill lift. This is done using also rippers and harrows. In compaction operation, it's very critical to calculate the volume of the excavated boro soil that will be enough for the compacted soil. For this calculation, we need first to have a formula to relate the soil density to the dry density. Starting with the moisture content formula, we can flip it to have the solids weights on the left side like shown. Then replace the water weight with the difference between the total weight and the solids weight. Then we can organize the relation to have again the solids weight completely on the left side. We know the dry density is the ratio between the solids weight and the total volume. So we replace the solids weight with the last formula we derived. We can group the division of the total weight and the total volume as the unit weight or dry density of the soil. So we will end up with the formula we need to relate the dry density with the soil density. Let's now see how we need this formula for the compaction boro quantity calculation. To find the compaction soil boro volume, we can relate the solids weight in the fill and boro states of the soil because this property doesn't change between the different soil states. The solids weight for each case can be calculated using the dry density, gamma D. But sometimes we don't have the dry density of the filled soil directly given from the soil report. Usually we are only given the density and the existing moisture content. So we will use the formula we derived in the previous slide to calculate the dry density of the boro soil, which we can use to find the soil boro volume that is enough for the fill soil volume. Thanks for watching this lesson video on compaction specifications and control. Check the other related video on compaction equipment to learn how to match the different compaction equipment to their appropriate soil types. Take care.